Hello and welcome back to the Cracking Fang YouTube channel. Today we're solving Leetcode problem 1514, path with maximum probability. You are given an undirected graph of n nodes, 0 index, represented by an edge list where edges of I equals AB, and this is an undirected edge connecting the nodes A to B with a probability of success of traversing that edge, success probability of I. Given two nodes, start and end, find the path with the maximum probability of success to go from start to end and return its success probability. If there is no path from start to end, then return 0, and you're only, okay, blah, 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 we don't care about that part. So let's look at an example. We have these three nodes, 0, 1, and 2, and we're given basically these edges and the success probability. So we can see that going from 0 to 1 is 0.5, same thing from 1 to 2, and from 0 to 2 is 0.2. And we're asked to go basically from 0 to 2. So you can either take this route here, and obviously this is going to have a probability of 0.2, or you can go first to 1 and then to 2. So this is obviously going to have 0.5 times 0.5, and this is going to equal to 0.25. So we're better off taking this route here because you have a 0.05 chance, higher chance of actually reaching it. So like with these problems, usually it's quite simple to actually figure out what you want to do on paper, but actually finding an algorithm to do this is not the simplest. Luckily, we kind of get an idea that, okay, we want to get between two nodes, and obviously each path has some sort of cost associated with it, and this should really just be ringing in your head that we want to use some sort of Dijkstra'S algorithm to find the shortest path. Obviously there's a cost here. So what we want to do essentially for this problem is we want to basically maximize the path that we can take such that we get the highest score, and we want to basically traverse the graph to, get there in the shortest possible time. So the first thing that we need to do is obviously build a graph. Build graph, where we're going to map for each node, we're going to map to a list of all the child nodes and the cost associated, or the probability of reaching that node. So we'll say child probability, and that's going to be the probability of actually reaching that child. So once we have that graph, we can actually traverse it. Now remember that we want to maximize our probability of actually reaching our final node. And what we're going to do here is we're actually going to make use of a heap. And the heap is going to tell us what the maximum probability is and what our current node is. So basically we always just want to go along the path that always has the highest probability, and eventually when we reach the end, then ideally that path should be the one that gets us there. So we're going to store on the heap basically the current node that we're at in the traversal, and then the cost so far. So the cost so far, and what we want to do is every time we're doing a new iteration of our heap, so basically picking which child nodes to go for a given node, we want to check, is going to that node going to be cheaper than actually going to that node by itself? And we need a separate data structure, which is going to actually map for a given node, what is the actual probability of reaching there from whatever the start node is. So this is going to map to some probability. And the reason we need this is that when we're at a given node, let's call it, node A, and we want to ask ourselves, should we go to node B via, this edge, and there's some probability associated with it. Is the current cost that we've incurred so far, the current probability, is taking this edge, so basically multiplying them, is this going to give us a higher probability of success than the probability of reaching this node on its own? So for example, if we look at so let's say to get to node C in this example, it's going to cost us 0.5, or the probability of getting there is 0.5. And that there's an edge from B to C, and the current path at B, maybe it's 0.75, right? But the edge from B to C only has a success rate of 0.1, which means that Let's just take our math here to make it easier. So this should be 0.5, right? So that means that we actually don't want to take this path because we can actually get to C cheaper from the start somehow. We don't exactly know what that path is, but there's no reason for us to go to B to C via this edge, because multiplying it by the cost of that edge will actually be would lower our current probability. So we don't want to take it. So we need this map to basically tell us whether or not we want to take an edge. If taking a given edge will actually improve our chances of getting to the next node, then we want to take it. We want to add, that current node and whatever the current cost is to our heap and keep going. And the problem will end when we actually get from whatever the start is to the end. So that's the general intuition here. A little bit messy, but just to recap, we basically need to have a graph, which is going to, obviously hold our structure here. We also need a heap to keep track of our processing through. In a standard BFS, we'd use a queue, but we want to use Dijkstra'S here because there's a cost associated with each edge, and we always want to obviously traverse the maximum probability of success. So that's why we want to use a max heap here to always be considering the maximum path that we can. And then we also need some data structure to basically tell us for each given node, what is the probability of getting there from the start. And you'll see how we use this in the code, but basically it was this example here where we check whether or not we actually want to take a node path. Okay, so again, it's a little bit convoluted kind of looking at it in this little example here, but let's now go to the code editor and walk it through, and hopefully it should become a little bit clearer, and we'll go through kind of the logic step by step. Okay, let's type this up. Remember that the first thing we need to do is build our graph. So let's now do this. So we're going to say graph is going to equal to default dict of list. Okay, now we need to actually populate the graph. So we're going to say for index, and we're going to pass in basically the node A, node B, or sorry, in enumerate edges, and you'll see why we need the index in a second. We're going to say that there is an edge from node A going to, okay, so it's going to be B, and then we also want to store the cost of going to that node, which is stored in success probability for a given node. It's going to be at the index I, so that's why we're going to say graph of so it's going to be success probability of I, and then we're going to have the opposite for the graph. So from B, we can also get to A, and the probability of that is going to be at success probability of I. So that basically represents the success probability of traversing this edge at whatever the index is. So now we have the graph built, and we need our data structure, which is basically going to tell us the cost of reaching a given node from the start. And remember, we're going to use this to actually evaluate whether or not we want to take a node as we're iterating through our graph and going through all of the possible options. So we're going to call this the max probability. And this is just going to be set to 0 because we haven't calculated anything yet. And we're going to multiply it by n to basically make it a list of length n, where each index will basically be, for a given node, the probability of reaching it from the start. Now we can set the max probability of whatever the start node is to equal to 1, because obviously the probability of reaching yourself from yourself is 1. You're already there, so it's just 1. Now we can actually start building our heap and essentially just going through the heap until we reach the final node. So we're going to say that heap equals to what? It's going to start initially at minus 1.0 because that's the probability that we start with. Obviously, we can't set it to 0 because then anything you multiply it by will be 0. So you have to start at 1. And the reason we do minus is because in Python, heaps by default are actually min heaps. And in order to get a max heap, we just need to multiply everything by -1 to flip it so that it operates as a max heap. So, and obviously we're going to start at the start node. We want to say this is start node. Okay. Now we need to actually just traverse the heap and until we get to basically the end node. So while the heap has elements in it, we're going to say that the current probability of our path and whatever the current node is equals to heap q dot heap pop. So we're going to pop from the top of the heap to get basically our best path so far, which has the highest probability, because again, we're trying to maximize the probability here. So it makes sense that we always focus on the top probability. Now, what we want to do is we want to say if the current node actually equals the end node, then we're done. We don't have to do anything else. We can simply just return the probability. And remember that we have it multiplied by -1 because we need the max heap. So we just need to flip it to basically undo that so we can return the correct result. So we're just going to do minus of whatever the current probability is. And in that case, we're done. We actually don't need to do anything else. Now what we need to do is we need to basically go through for our current node all of the possible options that we have in our graph and evaluate whether or not we want to take any of those and go down that path. So we're going to say for child node and then child node probability prob in graph of whatever the current node is. Current node. We need to check whether or not we actually want to go to that node. And the way that we're going to do this is we're going to say if the current probability, and remember we need to multiply it by negative to basically get rid of the minus here. If the current probability times the path probability is actually greater than the maximum probability of whatever the next node is, so the child node. And remember that this max probability stores the probability of getting to a given node from the start. If basically taking this edge that we want to take gives us a higher probability than the already calculated probability of reaching that node, then obviously this path is better because it has a higher probability. So we want to take that path. Otherwise, there's no reason to take it. We can just somehow get to this node from the start, going a different way. We don't exactly know what that way is at this point, but we don't really care. All we care about is whether or not taking this current edge is actually going to give us a better way of reaching the next node than if we had just gotten there in some other way. So if this is true, then we want to take this path. And we're going to update the max probability because obviously now we found a better one. So we're going to say the max probability of the next, it's the child node, is actually going to equal to, and then it's basically just this. So minus current probability times the path probability. And since we want to take this path, we're actually going to add this to the heap, and we're going to continue processing. So we're going to say heap q dot heap push. We're going to push onto our heap. And we're going to put, again, we have to then flip the probabilities again because we're working with a max heap. So be careful with your minus signs because you can kind of get an off by -1 error here if you're not careful. So we're going to put max probability of the child node and obviously the child node that we now want to process. So this will run basically until we either find the solution or the heap is empty and we were not able to actually, find it. This can happen if the graph is disconnected and there's no way to actually get from A to B or whatever the start to the end is. In this case, we simply just want to return 0 because there is no path. Okay, so let's just run this, make sure we didn't make any mistakes, and path prob, oops, all right, oh, sorry. This should be child node prob. Let's call this child. Yeah, okay, let's just use whatever we said here. Okay, sorry. That should fix it. Okay, cool. Sorry about that. All right, cool. That is accepted. Perfect. Okay, the last thing we need to do is simply define the time and space complexity. So the time, let's think about what we do. We build a graph and then we traverse this graph. So the actual building of the graph will basically be O of E, where E is the number of edges in the graph because we need to basically store all those edges. And then we also need to traverse this graph and we're basically going to be using this heap. So in the heap, obviously we have it, potentially in the worst case, all of the paths will actually have the same probability of reaching, right? They'll all just be 1 or they'll all just be some path. Actually, I think the worst case is 1 because it's just multiplying by 1 each time. So that means that we'd actually end up storing all of the nodes in our heap. So that means that we basically have, I guess we can call it v log v, where e is the number of edges, v is the number of vertices, right? So basically this is our time complexity. We need to build the graph, and then this is the actual traversal of the graph. And then for the space complexity, obviously we have, big O of E. Again, we need to build the graph, so we need to store all of the edges in the graph. And then we have the heap, which is always going to store, at most V elements, basically all of them. So that is your time and space complexity. Hopefully you enjoyed this video. Hopefully you learned something today. If you did, why not leave a like and a comment, subscribe to the channel to help me grow, and I'll see you in the next one. Bye.